Okay, so today I want to go over chapter 4, which is basically acids and bases. It's very much oriented towards organic molecules, as you'll see. I did put a video in the folder from Friday on just the basics of acid-base chemistry. So what's a conjugate acid, what's a conjugate base, and review from general chemistry. Some of this will be review, but most of it probably is going to be new and applying things that we've learned. So what I want to start with is this idea that we talked about last time, that if you take and you have an acid-base equilibrium, just a generic one, HA, going to A minus plus H plus, how do we shift this equilibrium to make a stronger acid?
We make the A component more stable.
Okay, so if we make the A minus more stable, then that's going to shift the equilibrium to the right, which is going to produce then more H plus, and then that's going to create a stronger acid. So anything we can do to shift that equilibrium, or anything we can do to make A minus more stable and shift the equilibrium, we need to do. Okay. Now the equilibrium, there is a Ka, there's an acidity equilibrium constant for this. And what we're going to do is we're going to go through sort of step by step this with me asking questions. So I will start with question number 1, which hopefully is going to be here. Okay. Okay, so I could send all these questions out at once, but I think we'll do them one at a time. So, question number 1. Question number 1 is this: we have 3 blanks here, and you have 4 choices to put in there. The blank, the pKa of an acid, the blank, the pKa, and the blank, its strength as an acid. So there's actually 2 possible ways to answer this. But fill in the blanks, the first, the second, and the third, with those 4 terms. It's matching. Okay. All right, so here are the numbers. And there's two ways to do this, so I'll go back and check the other ones later. All right, so let's do this in terms of the larger. So if you said the larger the pKa, then the smaller the acid, or sorry, the smaller the pKa, and then the stronger it is, its strength as an acid. So there's an inverse relationship between Ka and pKa, because if you remember, pKa is minus log of Ka. So the larger the dissociation constant, the stronger the acid, and then the smaller the pKa value will be. So we want to keep that in mind as we're going through. The smaller the pKa, the stronger it is as an acid, the larger pKa is going to be weaker. Okay. All right, so everybody okay with that? Then, let's see, what's the next question? So here are two. First one's a generic acidity equilibrium. The bottom's a basicity one. What I'd like you to do is match the terms acid, base, conjugate acid, and conjugate base to numbers 1 through 4 in those two reactions. Okay, let's see how we did on this one. Okay, so numbers 1 and 3 are the acids and the bases in in the forward reaction. So HA is our acid, B minus is our base. So those are okay. And then number 2 and number 4. So when you have an acid, A minus would be called its conjugate base. And then if you have a base, when it gains a proton, that's the conjugate acid. So what I like to do is I like to use the term, the way I'll sometimes say it is that, for instance, here A minus is the conjugate base of the acid HA, so that you know that HA is acting as an acid in that case. So for instance, if I said I've got carbonic acid, H2CO3, what's its conjugate base? HCO3 minus. Okay, so how did we get that? It lost a proton. And if I said, what's the conjugate acid of Cl minus? HCl. Right. Okay, so we need to know how we get those, and we basically get those by either adding or taking away a proton. All right, so that was number 2. Okay, question number 3.
So if you take away a proton, you get from an acid, you get a conjugate base, right?
Yes. Yes. The acid gives up the proton to become the conjugate base, and then vice versa for the conjugate base, or for the base becoming the conjugate acid.
So if you take a proton away from an acid, it becomes a conjugate base.
Yes. Okay, now let's look at this as a real live reaction here. H2SO4 plus carbonate. I want you to label one species 1, 2, 3, and 4. And I'm looking here at the forward direction as the point of emphasis, going from left to right. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? Oops, what was that? Oh. Okay. All right, so we have The most popular answer for number 1 is it's the acid. Before you even start labeling, what did you have to figure out in this case?
Where did the proton move?
So who's giving the proton up? Who's accepting the proton? Because that's the only way to find out if it's the acid or the base. So in this case, the H2SO4 is donating an H plus to the HCO3 minus to make H2CO3 and HSO4. And realize, I could switch acid, and the acid doesn't always have to come first. So with a problem like this, you want to make sure you figure out what's transferring the proton to figure out whether it's an acid or a base. So then number 2 is the base. So then 3 is the conjugate base of the acid sulfuric, and then 4 is the acid of the conjugate base, or the conjugate acid of the base, the bicarbonate. Okay. So that's the only thing new here is you might have to figure out where the proton is transferring. And if I just gave you this reaction, just the first part of it without the products, you'd need to have a chart to figure out which one's a stronger or weaker. We're not going to really do this because we're going to focus more. We're building up here. These problems should be getting sequentially harder. Okay, next. The periodic table. So you can tell a lot about the acidity from the periodic table. So which of the statements are true about the periodic table? And this has more than one true statement, so you want to mark each and every one.
Is chapter 4 going to be on the exam on Friday, or is it just 1, 2, 3?
Hold on, we'll talk about that. We'll talk about that in a few minutes. Okay, obviously the first one of the first two statements is true, and one of the last two statements is true, the way they're written. So for the first one, we have a 23 to 9 or 23 to 6 that A is true. And then for C, we've got a 16-13 breakdown, which is nearly 50-50. So for the first statement, is an increasing acidity going left to right, right to left? It's going left to right. So an OH, well, an OH is a weaker acid than an HF, for instance. And NHs and CH bonds really don't dissociate much. But I want to focus on this. I want to focus on the second one. Moving down, the acidity increases. Moving up, the acidity increases. What I will do, let's see, can I I wonder if you can change. Can you change your answers?
It says you just need full submission.
You probably have to hit resume.
Well, I'm going to resume, but has anybody changed their answers while typed in one thing and then gone back and typed in another? I guess we're going to find out whether you could do that or not. So I will hit the resume button. And what I'd like you to do is take a minute to discuss with somebody close to you in space, and then we'll revote.
That's an activity.
I didn't get that off the top of my head. When you think about it, it makes funny sense. Because he was like, he's like a cast from like a strong acid does not give up.
Like, the way I know it,
Oh, what's to
HCl.
stay? So, I actually think those increase the cost and increase the outbreak.
Okay, you ready to revote? I saw numbers change, so I think you can revote on the last two. Go ahead and revote on the last two. It won't show up here that the 30 is not going to change, so I'll give you another 15 seconds to revote if you want to change. Well, everybody decided to revote, but the first one to make it absolutely correct. Okay, 25-5. So we moved in the direction of going down the periodic table, increases acidity. I heard some electronegativity. I heard that the difference between HF and HCl. So what do you remember about HF? What does that mean? Okay, so that means it only partially dissociates in water, so that we have equilibrium arrows. So that would make HF a weak acid. If you went back and looked at your general chem notes, you'd see that you did a lot of ice charts with HF because it was a weak acid. Remember the initial change, equilibrium with X's and stuff like that, those ice charts. But HF is a weak acid. HCl is a strong acid. What does that mean? It means it completely dissociates in water, sort of. Because here's the issue. If I have F, Cl, Br, and I, going down the periodic table does increase in acidity. But you might say, how do you get more than 100% dissociation if HCl completely dissociates? Does that mean that HBr more completely dissociates and HI even more completely dissociates? It basically means that HCl doesn't completely dissociate. It's got a very high equilibrium constant. I think the table's actually in the book. I think they went 8, 9, and 10. So that 10 to the 8th, 10 to the 9th, 10 to the 10th. So they don't completely dissociate, but HI does dissociate a lot more than HBr, a lot more than HCl. But in general chemistry, we consider them strong acids and completely dissociate. Okay. So then going with our O, our N, and our C, the acidity increases that way. so that an OH bond is weaker, or well, H2O is weaker than HF. If you put a nitrogen species in water, it doesn't act as an acid, right? It absorbs a proton, or it accepts a proton from the water and becomes NH4+. So nitrogen doesn't act as doesn't really act as an acid. And carbon-hydrogen bonds, they're not going to dissociate at all. Okay, so that's the periodic table, and we're going to use this over and over again. And we're going to also have to be able to use the periodic table for basicity. So that if I said, which is a stronger base, N- or O-?
N minus.
It's N- because the O-, because H2O is a stronger acid than nitrogen, and so that means nitrogen will have the stronger conjugate base. So we're gonna basically put together a table that looks like this. H- and C- are the strongest bases we're going to be able to make in this class. Okay. Then N-, then O-, and then F-, and then Cl-, Br-, and I-. Okay. So we got to be able to go both. We have to be able to talk about basicities and acidities. Okay. Next. Equilibrium pushing. What is that? And all these questions I wrote after going through there, so I wish I had a good database. I wish the book had this good of a database where I could just pull these questions out and not have to think about them, but sadly that's not the case. Okay, one statement is true about trying to push the equilibrium, or about how the equilibrium is pushed. Is it pushed to the side with the weakest acid-base pair, towards the side with the strongest acid-base pair, or you can't tell? Okay, here's our responses. Majority say that it's going to be pushed towards the weakest acid-base pair. And that's correct. So when you're looking at an acid-base equilibrium, in the forward direction you'll have an acid and a base, and in the products in the reverse direction you'll have an acid and a base. So what you do is you find the acid on both sides and compare, and so the equilibrium will be pushed towards the acid that is the weakest. And these never go against each other. So if you have the weakest acid on one side, the weakest base will also be on that side as well. Because otherwise, it would be extremely difficult to tell where the equilibrium lies. So then the next question is, well, how would you determine what the strength of the acid is? And so here's a reaction that has 2 pKa values listed. So where does the equilibrium lie here? To the left, right, or right in the center? 25 people say to the right. So what's the reasoning for this? Okay, higher pKa means it's a weaker acid. So of these two, NH4 minus or NH4 plus is the weaker acid. And so the equilibrium is going to be pushed in that direction. Okay, next one. Okay, the next one is you have 3 acetic acids. This is acetic acid, 2-carbon acid. One has a hydrogen here, one has a chlorine, which one has a fluorine, or then has a fluorine. So there's three substitutions, H, a Cl, and an F. Over here you have 3 pKa values. Match them up. And if you're looking at this, this is pretty much a rank the 3 acids from strongest to weakest, sort of.
Where is the F and Cl coming from?
So in other words, this X is either an H in both cases, a Cl in both cases, or an F in both cases.
Okay. Oh, that was an equal. I thought that was a double bond sign. Okay.
No, it's just an X. X stands for that.
Yeah.
Yeah, no, we can't do that. Okay, let's see what the response. Let's get out of this and let's see what the overall. 30% correct. It's not bad. It beats the 15% this morning. Okay, here's my questions. Of the 475, 2.6, and 2.87, which one is the strongest acid? 2.6 is the strongest acid. And then what do you think is the strongest acid? I'll pull. Because I think I know what these statistics mean. The weakest acid is, how many people say H is the weakest acid? Okay, so that's what the 24 is. But it looks like we have a split between Cl and F. So how many people think that Cl was the strongest acid? F was the strongest acid. Oh, I guess we don't have the split. Okay. So this might be too early of a question, but I'm going to ask. Well, it was in the reading, so I'm going to ask it anyway. So here's my equilibrium. To form the O minus, plus then the H plus. So what you're saying is that if I replace this hydrogen with a Cl, that you get a stronger acid. That's what all the hands in the air meant, right? That the one with the Cl is the strongest acid of all. Why? What's your reasoning for that?
Because chlorine is typically a weak acid. We're looking at like the trend.
Okay. What other reasonings did you have?
We just talked about the size. That's the acid. But I think that was a slightly different context.
Yes. The size of the atom is in the context of when it's directly attached to the hydrogen. This isn't. Let me take you back to the first principle I started class with. I know, it was a long time ago. What was it? If you want to push the equilibrium to the right, you got to make the conjugate base more stable. So if substituting Cl on here is making this shift more to the right, which would make it a stronger acid, how is the Cl stabilizing the conjugate base?
It's less electronegative than chlorine.
Let's not talk about fluorine. Let's just talk about how chloride does it. You were stretching? Were you stretching?
No.
Okay.
Because there's a larger amount of electron density in Cl, it would allow for some density to be shifted over towards the oxygen to compensate for the loss of the hydrogen. Or really, it's going to be shifting over to the carbon.
Yeah, I like the other direction.
Yeah.
Did anybody understand that? It's okay.
A whole nother.
It's okay, I did. I understood it. Here's Cl is delta minus. Why is it delta minus? Yes, but where did it get its extra electron density from?
Has bone pairs.
It's getting extra electron density. So where is it getting it from? The carbon. So the chlorine is delta minus because it's taking away some electron density from the carbon. Now, in order for this carboxylate, this deprotonated carboxylic acid, to become more stable, I have to move electron density from the O minus, and I want to spread it out throughout the molecule. That would normally be called delocalization. Right? I want to spread out the charge. And the more I can spread out the charge, the more stable the molecule becomes. So what's the chlorine doing? It's pulling electron density away from the carbon, which allows then some electron density to be pulled from the carboxylate, from the O minuses. So I'm spreading out the negative charge in the molecule, and that's going to make it more stable.
Okay, why is it making it more stable?
Because I'm spreading the charge out. So the chlorine is taking on some of the negative charge from the oxygens. It's just the oxygens, some of that negative charge is going to the carbon to sort of replace what was taken up by the chlorine.
So even though you're spreading out the charge, it's still gonna have a full octet, right? Like the elements that can't have a full octet.
Yes, everything's got a full octet. It just means that there's the negative one charge here is now being spread out throughout the molecule. So this extra delta minus is probably going to be a little bit of the charge on the oxygen. And actually, that would be the resonance hybrid for the carboxylate. So really you have to think of it as all -1. So the more I can spread that charge out, the more stable I make the deprotonated carboxylic acid. The more I can spread it out, the more stable it is, the more the equilibrium shifts to the right, and the stronger the acid. Does that kind of make sense? That's what's happening.
And then the difference between the chlorine, why it's a little bit more stable than the fluorine, is because fluorine's taking so much of it away, it makes it.
Well, I didn't say anything about the fluorine being more stable. You said that. I know. So my next question is, if chlorine does that, wouldn't fluorine be better at it? No, I mean, if chlorine's good at it, fluorine's got to be better. Why? Because fluorine is more electronegative. So that means fluorine can pull even more electron density away and can stabilize this even more. I never said chlorine was the strongest acid. You guys did. That's okay. This morning one person had fluorine. But they were right. So fluorine is actually the strongest acid, because the fluorine then is able to pull more electron density away from the negative charge. Does that kind of make sense? So for these acetic acids, the more halogens you put on the carbon, the stronger you can get it. You can get the acid. Like acetic acid with just an H there, that's vinegar. right? In lab, that was the product that we made in the microwave, right? If you get even some concentrated acetic acid on your skin, it might get a little irritated, but I mean, acetic acid's vinegar. You get trifluoroacetic acid on your skin, then you're going to have a little bit of a hole. Well, trifluoroacetic acid is what they use to burn moles off. And so it's a very strong acid. And I may have a couple scars where some trifluoroacetic acid bottle fell down on the floor and sprayed up. I must not have been wearing long pants that day. My safety violation. And the next thing I know, there's a couple of holes there. And then I get infected, and then, what that. So this is pretty potent stuff. But the idea here is I'm stabilizing this by spreading out the negative charge as much as possible. So for that question, fluoroacetic acid is stronger than chloro, which is stronger than H, which is stronger than just basic one. So when you have a molecule in an acid-base equilibrium and you have a negative charge as the conjugate base, anything you can do to spread that charge out is going to stabilize that anion. Vice versa, if we were talking about KBs, and we were making a positive species as a product, anything I can do to push electron density towards that positive charge is going to stabilize. So when I have a negative charge, I want to pull the electron density away from it. When I have a positive charge, I want to push the electron density into it. And so by changing my functional group, I can make that happen, and I can make the acid become stronger or weaker. And so in this case, fluorine is the strongest down to hydrogen, which is the weakest. Okay. So it's electronegativity, it's not size. Okay. Which then gets us to what would be the last problem where, there's actually 4 more problems that I have, and it's important to remember what I just said, which was what? What? 4 more of these. So, that's what I just immediately last said. But the principle I said before that was, if you've got a negative charge, pull the electron density away from it, makes it more stable. If you have a positive charge, push it in. But I do have 4 more of these problems. And what I'm going to do is I'm going to figure out how to get them into, I guess, I'm going to put them at the end of the chapter 4 in-class reading problems so you can do them. And then, if necessary, we'll talk about them in class, or I can do videos on each one and put them on the discussion groups. So I'll send you an email out on when they are. Chapter 4 is not on Friday's exam. Up through chapter 3. Chapter 4 will be on the next exam.
So what's the distribution? Is it going to be probably below chapter 2 because that's what we spent the most time on?
It'll be naming, it'll be Lewis dot structures, it'll be resonance structures, it'll be a mix of everything.
Can you post a video on how to do resonance structures?
Yes, there probably is already one on there, and there's some problems in the early first 2 folders. But yeah, I think I have that, but I can point them out to you.
Okay. So if I can't find them,